Hello everyone, my name is Hirschorn. I'm a PhD student here at Tel Aviv University under the supervision of Professor Shai Avidan, and today I'm excited to share with you our recent works about category-agnostic pose estimation. So let's begin with a brief overview of what pose estimation is and its uses. The goal of pose estimation is to determine the location of object's key point in an image. Now, these key points are not isolated. We can connect them through the 3D structure of the object. So if we treat these key points as nodes and to the connectivity as edges, we can define a graph, which we term a pose graph. Now, this pose graph can serve as a powerful way to represent the object, and it has various advantages over using just the pixels. First, pose graphs abstract away details like lighting conditions, camera angle, background, and other appearance-based features that might be not relevant for our task at hand. Second, they are extremely compact, as they are just composed of the 2D coordinates in the image. And despite their simplicity, they are rich in semantic information. For example, in the video here, looking only on the right video of the pose graph representation, we can detect a person that is doing various activities, even without looking on the full video on the left. Recently, pose graphs have become a useful tool for generative AI. They are used to control the generation of images, guide the motion of videos, and more traditionally, pose graphs are widely used in fields such as video analysis, robotics, augmented reality, and zoology. It's even been implemented for sports and was integrated to detect offside position in the 2022 FIFA World Cup Championship. This versatility makes them valuable across all these diverse tasks. So, considering all these advantages, a model that can locate key points for any object category can be extremely valuable. However, traditional pose estimation models are designed to work only on one specific object category. For instance, a model trained to estimate human face key points requires a dataset of annotated human face key points with a set of predefined key points. Similarly, if we want to detect key points for sofas, we need to go through the same framework of collecting a dataset, annotating the key points, and then training a completely separate pose estimation model. This category-specific approach becomes a major limitation when we encounter object categories that we have only limited training data for. Or maybe we want to detect key points that are different than the one annotated in our dataset. So this limitation raises the question, can we train a model that can generalize to new object categories? The answer is yes, and the solution is called Category-Agnostic Pose Estimation, or CAPE for short. CAPEs allow us to predict the key points for any object category using just a single model. It works in a few-shot manner, which means that it can generalize to new object categories given just a few examples. We train one model on a diverse set of categories, and then during inference, our model should be able to handle categories it has never seen during training. This approach is powerful because it significantly reduces the cost of data collection and model training or fine-tuning. So here's how it works. We begin with a set of support images from a new category. These support images can be as few as only one image. Then the user defines the set of key points that you wish to locate in this new category. And the key point definition is highly flexible. It can define any number of key points they find relevant for their task at hand. And once they have the support image and key point definition, they can input query images from the same category. And then our model should be able to detect these key points in this new object category. And traditional CAPE models usually do it by matching key points from the support image to the query image patches in a latent space. However, these methods overlook a critical aspect in the images, which is the geometrical relations between the key point definition. Geometrical relations are crucial for improving key point localization, especially in challenging scenarios like key points that are symmetric or partially occluded. For example, if we know the location of the blue key points here in the image, we can make an informed guess where the red key points should be, even if they are not clearly visible. This is because structurally connected key points tend to be adjacent to one another. So our key insight is to leverage these relations. And using the connectivity as an additional input, we can define the input key points as a graph. So here's an overview of a common CAPE framework. We start with a pre-trained backbone in order to extract features from the query image and from the support image. Then we are left with the key point features and the query image features. We then refine this feature using a transformer encoder. And once we have the refined features, a similarity proposal generator makes an initial guess where the key point coordinates should be in the query image. And finally, a transformer decoder refines these initial guesses to predict the final key point locations. So our idea was to incorporate the structural prior into the transformer decoder. The inputs to the decoder are the key point features, the query image features, and the initial guesses. And the decoder should use this information to iteratively refine the guesses until it outputs the final precise location of the key points in the query image. The decoder is composed of three main blocks: a self-attention block to exchange information between key points, a cross-attention block to exchange information between the key points and the query image, and a feed-forward network. And we make a simple yet highly effective architectural change. As we now possess the graph connectivity as an input from the user, we treat the input as a graph instead of isolated key points. So we can replace the feed-forward network, which is just a common MLP block, with a graph-based neural network. Actually, all we did was replacing the first linear layer of the MLP with a graph convolutional layer. This results in processing the key points as a graph instead of isolated key points. And this adjustment may seem small, but it leads to a noticeable performance improvement in the accuracy of the model. So let's explore the difference between just using self-attention to exchange information to using these graph convolutional layers. The self-attention matrix is computed by embedding key points through a key and query matrices to compute the self-attention matrix. Now, from a graph perspective of the self-attention mechanism, it can be viewed as constructing a fully connected graph, where each key point is connected to another key point, and the weight of the edges connecting each two key points is determined by the self-attention matrix. Now, focusing on a single node, we can demonstrate how information propagates between two different key points. Each node receives inputs from all other, weighted by their corresponding attention values. However, for a new unseen category that the model has never encountered during training, it's challenging for the model to predict the correct structural connectivity, the one that can help him differentiate between symmetric key points or partially occluded ones. So structurally connected nodes that are close to each other physically in the object should play a larger role in feature propagation. So now, let's assume that we are given a prior structure from the user. How can we incorporate this structure knowledge to the transformer architecture? Our idea was to use this connectivity information in the form of a graph. And using graph convolution, we can leverage this information. So here, graph convolution propagates the information between neighboring nodes, focusing the exchange of information based on the structure. Sharing information in our context is like sharing location cues. So this enables the model to respect the natural structure, resulting in improved localization. So to train and test our model, we use the dataset called the MP100 dataset. It is a dataset that is composed of over 20,000 images from over 100 distinct categories, ranging from animals, vehicles, furniture, clothing, etc. It is splitted such that during test time, we are encountered with categories that have never been seen during training. And additionally, the MP100 is actually a dataset that is constructed from existing category-specific datasets. As we now require also the graph definition between the key points, we just took these definitions from the original dataset, and in the few cases where the graph definitions were missing, we annotated them ourselves. So this small change achieves state-of-the-art results for accuracy, and I think that the qualitative results highlight the benefits of incorporating this structural prior. In the first row, we can see an example of symmetry breaking, where previous models struggle, but our model successfully differentiates between symmetric key points. And in the second row, our method shows superior performance in maintaining structural consistency. We also evaluated our network on images from different domains. So our model, that was trained only on real images, demonstrated adaptability and effectiveness working on images that are cartoons or text-to-image generated images. And furthermore, our model actually performs well when the support and query images are from entirely different domains. So using a graph structure improves localization, but it also introduces a new limitation, which is the choice of the graph itself. Different graph annotation can result in different localization performance and accuracy. even when using the same images and the same key-point definition. So this raises an interesting research question. What is the best pose graph we should use? And the answer depends on the task at hand. For our purpose of localizing key points, the best graph is the one that most effectively aids in localization. So as part of our follow-up work, we develop a new method which predicts the optimal graph for localization. We maintain the same general framework as before, improving various components which we outlined in the paper, but our main contribution is in solving the task of predicting the best pose graph. However, predicting an entirely new graph structure is challenging, especially when we should be able to encounter categories that the model has never seen during training. It requires prior knowledge about the object's 3D structure or the object's anatomy, which is hard to predict. So our solution is simple yet effective. Instead of trying to predict an entirely new graph, we focus on refining prior input graphs. So the user provides an initial unweighted graph, just like before. But now our model refined this graph and predict weights on the edges, making the graph more task-specific and accurate. So here are some examples of the graph predicted by our model. On the left, you can see the input graph, which is the graph input from the user, which is unweighted. And on the right, the predicted graph by our model. On the top left example, the model assigns lower weights to symmetrical key points on the table. And on the bottom left, the model adds new edges to the graph in the human face where they were missing, helping localization. On the right, we see a nice example where our graph prediction model predicts different graphs to two different instances from the same object category. And this adaptability allows our model to handle a wider variety of scenarios effectively. And of course, this graph refinement results in a significant performance in accuracy, achieving a new state-of-the-art result compared to the previous methods. So to conclude, we've introduced a novel approach for category-agnostic pose estimation. We started from isolated key points to unweighted graphs, and finally, in our latest work, to adapted weighted graphs. And this method takes full advantage of the geometrical structure within the objects. We've also updated the MP100 dataset to include graph annotation for all categories, providing a valuable resource for future research in CAPE. This contribution demonstrates the potential for a more adaptable and versatile pose graph applications in computer vision. Our code, demo, and data are publicly available, and we invite you all to explore our paper for further details. Thank you.
Thank you very much, Or. Any questions from the crowd?
Yes, I have a question. Great work, Or. So I wonder if you can do cross-domain posing. Let's say my query image, let's say my reference image is the pose of a chair, and I would like to pose as a query an animal.
So this is a great question, and the reason is that we did try it, and we show it in our paper. So we tried an example where our support image was a chair, and we tried to detect the key points in a horse. So we saw that our model was able to match the legs of the chair and the legs of the horse and the base of the chair to like the upper part of the legs. It has these limitations, but actually our model was able to correctly understand the 3D orientation of the objects. So it did manage to create some kind of an embedding where it broke symmetry, but it's of course limited to the connections that are reasonable.
Okay, thanks. And another question, let's say I have an image of an object and I would like to find the pose of a 3D object. Have you thought about that extension?
So it's an interesting extension. We only work on 2D coordinates, but I think a natural extension would be to understand the depth of the image and incorporate it to our model. It's a nice follow-up research that we haven't had the time to explore yet.
Maybe in a collaboration.
Sounds great, thank you.
Okay, there is another question here.
Hi, very nice work.
Thank you.
I was wondering, probably the influence of the graph connectivity is highly dependent on the feature extraction, like which backbone are you using and how much it knows about the world and semantic. So I was wondering which backbone have you used, and have you explored this? Like if you are using diffusion features or a dyno that already has a lot of information about the world, is it still influential?
Yeah, so it's something that we spent a lot of time experimenting with. In our first work, we used swing transformer encodings. We did try dyno, but it didn't work as good as the swing one. But in our follow-up work, we managed to find a way to incorporate the dyno features, which have great generalization abilities, to work for high accuracy localization. So in our latest work, dyno V2 were the feature that we used. We haven't tried stable diffusion features. I think the main reason is that a main obstacle in this kind of line of work is symmetrical key points, and stable diffusion usually is not really great in differentiating between left and right. But I think that fine-tuning the model, especially when using dyno feature, is the right way to go.
Thanks.
Okay, so thank you very much.